Okay, so it's week four Monday. Happy Monday, you guys. That means we're halfway through the course. I'm shifting a couple of the topics around, uh, I'm trying to get things to line up a little bit for the summer. So I know last week, we started talking about maximum likelihood estimation, and I think that's fine. We might come back to that topic later on in the quarter. So I'm just moving a couple topics around. I'm going to go ahead and we're going to move on, and we are going to start talking about the Bayes classifier. Okay, so we're going to start introducing classification methods, and so if you have the textbook, last week we left off in chapter 2, which was about maximum likelihood estimation. I am skipping chapters 3 and 4 entirely, which is about Bayesian statistics, and then we're going to jump into chapter 5 today. Okay, chapter 5 is about classification problems, and so that is that's the topic for this week, and your homework will deal with classification. And so so classification is all about trying to predict the class of some object. Okay, and so what we have is we have training objects. Okay, we've got n of them. And the training objects exist in dimension D. Okay, so we've got each. So maybe I think in today's examples, most of my objects will be two-dimensional objects. But then in your homework data set, you're going to be dealing with four-dimensional objects. So you will have the iris data set, and I'm not sure if you guys have worked with the iris. Have you seen the iris data set from Fisher's iris data set? So a lot of you, I think, are familiar. It's a favorite among machine learning because there's 3 defined classes, and then you have 4 numeric variables, things like petal length, petal width, sepal length, and sepal width, and they measure those 4 numeric variables. And so your objects are in 4-dimensional, and each observation is has four measurements right there. Okay, and then and each of those objects is associated with some kind of class label. And so for the iris data set, the class labels are the 3 species, which are Setosa, Virginica, and Versicolor. We'll just do some simple examples today. We've got these 2-dimensional objects, and I'm going to just kind of label them, with different colors and stuff like that. But whatever we have, we've got these d-dimensional objects. You get some kind of class. Okay, the class labels, we often represent them with integers, but we have to remember to treat them as categories. Okay, so we label them 1, 2 up through letter C. And what we want to do is when we get a new object, we want to predict what class it belongs to. But even though they're labeled as numbers, we don't treat them as numbers. Okay, class label 2 is not twice as big as class label 1, and there's no meaning to having a class label like 2.5. It's got to be just one of the categories here. Okay, and so the first classifier that we're going to look at is the Bayes classifier, and then we'll develop this into the naive Bayes classifier. Okay. And it's called the Bayes classifier because it uses Bayes' rule in probability to find kind of the probability that an observation belongs to a certain class. Okay, I should say there's also an important classifier that we won't talk about, which is logistic regression. I think you guys cover logistic regression in 100C. Is that right? In 100C, you guys cover logistic regression? Yes, no, maybe? Or maybe 101A? Logistic regression does not sound familiar for 100C. Okay. Well, let me change it to you can chat to everybody. Okay. yeah, logistic regression. Well, maybe 101A. I don't know. Okay. Well, anyway, that's another popular choice for classification, but we're not going to spend time on it here. Okay. The Bayes classifier is what we call a probabilistic classifier. Okay. And what it does is it returns a probability. And so if you have three classes, it's going to return a vector of probabilities. So let's say you have class A, class B, and class C. You know, one possible result is it's going to say class A 19%, class B 80%, class C 1%. Okay, and you know those percentages add up to 100%. Okay, logistic regression is limited to just having two classes, a yes or a no, and it's going to be like 80% yes, 20% no, or 5% yes, 95% no, or something like that. Okay, there's other classifiers such as the k nearest neighbors and those things, and those use what we call hard classifier rules, and they designate a class without an associated probability. Okay, so it'll just say like this belongs to this class or this belongs to that class. Okay, and so we'll take a look at that, and that's k nearest neighbors and support vector machines, and we'll take a look at those on Wednesday. Okay. And even though we're using Bayes' rule, this is not considered Bayesian statistics, okay? Bayesian statistics, the primary idea is that you're treating these unknown parameters as random variables rather than fixed values. That's something that I cover in 102C, but that's not part of this, okay? All right, so if you recall, this is Bayes' theorem. Bayes' theorem says the probability of A given B is the probability of B given A times the probability of A divided by the probability of B, okay? The numerator, okay, the probability of B given A times the probability of A is equal to the probability of B and A, or B intersection A, okay? And then if you recall, that's just all of your probability rules, right? So this is from 100A, I believe, right? You have the law of total probability. So this denominator, probability of B, can be decomposed into basically the probability of B given A, which is the probability of B given A sub n times the probability of A sub n for all possible kind of values of A, right? So it's going to be, you know, what's the total probability of getting a queen in a deck of cards? What's the probability of getting a queen? It's going to be the probability of getting, you know, a queen if it's a, you know, the sum of the probability of getting the queen of hearts plus the probability of getting the queen of spades plus the probability of getting queen of diamonds plus the probability of queen of clubs, right? You have to add up all kind of subsets of those things, and when you combine them, you get the total probability of B, right? So I'm hoping this all looks familiar as far as remembering the rules of probability from either Stats 100A or Math 170, whatever letter it is. Okay. And so, you know, this denominator is equal to the numerator summed across all possible values that A can take on. Okay. And so, you know, the goal that we're going for, all right, is a conditional probability. Okay. It's a probability of that T belongs to, is equal to certain class C. That's the probability that the new observation belongs to a particular class given the kind of the numeric values inside of X, right? So whatever, you know, given these four measurements, the petal length, petal width, sepal length, and sepal width, what is a probability that that these observations are a flower of this class? Or, you know, given these values, what's the probability that it's class A or class B or class C? Okay. And then the other things that are given to us are the training data, which is the values in X in the training data and the labels in the training data T. Okay. So this is, we want to know the probability that the class label T is equal to some class label C given the values in the input vector of the new observation X new, and all the values in the training data and all the values in the labels on the training data. Okay. So using just kind of applying the rules of probability, and then later on we'll apply Bayes' rule. This is kind of what we can do, right? So we know that this probability, whatever it is, has to be between 0 and 1 because it's a probability, okay? And then we also know that because if we have C different classes, okay, that if I add up all of these things, because they're probabilities, they have to add up to 1, right? If we cover all the possible classes, as long as we get them all, then we know that they have to sum to 1, okay? All right, and so all we do is we're going to just apply Bayes' rule, and we're going to say the probability of A given B is B given A times the probability of A divided by the probability of B, okay? So A is going to be T nu equal to C, and then the given B is going to be X nu. So when I flip this around, this becomes a probability. So this is what we want. The probability that some new observation belongs to class C is equal to the probability of X nu given T nu equal to C times X and T, right? Or and X and T. So this is what we call the likelihood, okay? This part is the probability of getting these observed values X nu given, or if we assume that the new observation does belong to class C, okay? So what's the probability of getting X nu if the new observation does belong to class C, right? And those probabilities, this probability is based on the training data X and T, okay? We're gonna multiply that by basically the probability of A, which is probability of T nu equal to C. This is what we call the prior probability. This is the probability that the new observation belongs to class C, okay? Belongs to class C before we know anything else about it. Just before we know anything else about it, just given kind of the training data X and T, what's the probability that some new observation belongs to class C, okay? So this question doesn't, or this probability does not involve the values in X nu, okay? And then we divide this by the probability of X nu, okay? X nu is the probability of getting the values in our vector X nu regardless of the class label. So there's no class label T nu equal to C. It's just whatever class label, whether it's class A, B, or C, what's the probability of getting the values that we observed X nu, okay? And again, those probabilities are based on your training data X and T, right? So, so I hope, you know, the application of Bayes' rule applied to this looks like this. I know this thing can look a little intimidating at first, but if you just break it down and say, well, we're going to call this part B, this part A, then I hope this makes sense. Okay. And so what we can do is we can apply the law of total probability. Okay, law of total probability that says the probabilities across all the possible classes, they have to add up to 1, right? So just applying that, we know that this denominator, this thing, probability of X nu, this is going to equal the sum of the numerator across all possible classes, right? So this thing, the probability of X nu, okay, is going to equal whatever this numerator is across all the different possible classes C, okay? So whatever classes you have, class A, B, and C, or whatever it is, this is going to equal the numerator summed across all possible classes. So we're going to say it's the sum from basically class 1. We're going to apply this from class 1, 2, 3, 4 up to letter C of just the numerator, okay? And to kind of just make sure that we're not getting this and this mixed up, I'm just going to call this C prime, okay? So it's going to be the probability of the numerator summed up across all the different possible classes. So I'm just applying probability rules here. I think, so I hope you guys are following this, but if you're not, I hope when I just do a problem with this will make sense. So I'm going to just do a simple example of the Bayes classifier, and it's going to look like this, okay? So let's say I've got my my pouch. It's got some red and blue marbles, okay? Actually, we're buying a whole bunch of these pouches, okay? We're buying a whole bunch of these pouches. We're going to have 25 pouches, and we went online, okay? And then when they arrive, I don't know, the pouches are labeled and they say, oh, this one came from factory A, this one came from factory B, this one came from factory C, et cetera, et cetera, et cetera, okay? So they're filled at different factories. And then, you know, as we open up, you know, we say, oh, you know what, these factories actually are a little bit different, okay? So out of the, we're gonna say we have 24 of the pouches are labeled with their factory, okay? 12 came from factory A, 6 came from factory B, and 6 came from factory C. And then the last one, the 25th one, is not labeled. And what we're gonna do is we're gonna try to guess what factory it came from. Okay, and so we're gonna assume the bags are filled with some kind of, you know, Bernoulli or binomial process that, you know, every time it puts a marble in, there's an equal chance of it, and not equal, but the probability of being red or blue, you know, that probability remains constant. Okay, so, you know, 25 bags of marbles, 24 of them are labeled A, B, and C, and then we've got one that's not labeled. That's going to be our test case. Okay, and we're trying to figure out what probability comes from what's the probability that, you know, this marble came, this bag came from factory A, B, or C. Okay, all right, and so we go through and we count up all of our data, right? So we dump out the bag. We say this bag came from factory A. Let's count up how many are red and how many are blue. And we look at all the pouches that came from factory A. And overall, after summarizing all of them, okay, when we look at all 12 pouches, we find that 60% of the marbles are red, and then the other 40% are blue. And then when we look at the 6 pouches that came from factory B, 50% are red and 50% are blue. And we look at the pouches that come from factory C, and 40% are red and 60% are blue, okay? So, you know, we don't work at the factories, so we don't actually know the proportions that, that the factories use to fill up the things, right? So, you know, it's possible that the factories all use the same proportions. It's possible that, that they're different, you know. So we're just, you know, the different pouches, you know, that come from the same factory exhibit variation, but, you know, they don't cause us concern about whether, about assuming that the marble selection is a result of a binomial process. And so, you know, it's possible, you know, we could say, you know, one pouch from factory A is 40% red. Okay, another pouch from factory A is 55% red. Okay, and, you know, these are all high likelihood outcomes, and so we're not going to worry about the binomial assumption, okay? And so, so these things, when we say, you know, 60% are red, you know, when you do probabilities of maximum likelihood estimation from sample proportions, then your sample proportion ends up being the maximum likelihood estimate, okay, from your training data. Okay, so this is kind of the setup, and what we do is we're going to go back to this test case, all right, and we open it up, right, and when we dump it out, 50% of the marbles are red, right? 10 are red, 10 out of the 20 marbles are red, okay? And so we want to know what's the probability it came from factory A, factory B, or factory C, okay? So again, remember, factory A is 60% red. So far in our observed data, factory A is 60% red, factory B is 50% red, and factory C is 40% red, okay? And so what we're gonna do is we're going to calculate the likelihood. The likelihood is, what's the likelihood, or what's the probability of getting the observed data of 10 out of 20 being red, okay? If we assume it comes from factory A, or if it comes from factory B, or if it comes from factory C, okay? And so for this, we just use the binomial probability. And we say, if it came from factory A, where 60% are red, then the probability of getting 10 out of 20, 10 red out of 20 is going to be 20 choose 10, 0.6 to the 10, 0.4 to the 10, and that turns out to be 0.117. If we say it came from factory B, okay, which produces 50% red, you know, what's the probability of getting 10 out of 20 red? We do this calculation, we get like 17.6%. What's the probability it came from factory C? Factory C is 40% red, so 20 choose 10, 0.4 to the 10, 0.6 to the 10, and we get, 11.7% also, right? So this is the likelihood of our thing, and what we find is that, could this pouch that got 10 red out of 20 marbles, could it have come from factory A? It could have. If it came from factory A, what's the probability that factory A, which is 60% red, produces this thing? It comes out about, the likelihood is 11.7. Okay, factory B has the highest likelihood at 17.6%, okay, which makes sense because, according to our training data, factory B produces 50% red, and that's what we have in our pouch. Okay, our pouch ends up being 50% red, and so we say, okay, this has a high likelihood of coming from factory B. And then factory C, which produces 40% red, what's the probability that it produced our pouch, which was 10 out of 20 red, and that's 11.7%. Okay. And if we were just using maximum likelihood estimation, or just kind of a maximum likelihood, we would say, oh, factory B is the most likely, okay? Because based on this, your pouch is 50% red, B produces 50% red. It just makes sense that we would choose factory B, okay? But with the Bayes classifier, we don't just take into account the likelihood, we also take into account the prior probabilities, okay? So before we even opened the bag, okay, before we opened the bag and found that they were 10 red out of 20 marbles, okay, what would we have guessed, right? What is the probability that it came from a particular factory? And so the prior probability is the probability that a new observation belongs to class C, basically before you open it up, before you look at the data inside, okay? So this is based only on the training data before you actually look at the contents of the pouch, right? And so on the training data, it would have been reasonable to think it came from factory A with probability 0.5, because when we got the 24 pouches, 12 of them came from factory A. So maybe it's reasonable to think that factory A is the kind of the most likely producer of marbles or whatever. And so 12 out of the 24 came from that factory. So we got our prior probability is 50%, okay? Whereas 6 came from factory B and 6 came from factory C. And so our prior probabilities for factory B and factory C are 25% each. Okay, I hope that makes sense. And so what we're going to do is we are going to multiply those two together. Okay, we're going to take the likelihood and we're going to multiply it by the prior. Okay, so the numerator for each of these classes is the likelihood, the probability of getting that result, 10 red out of 20 marbles, multiplied by the prior probability that it belongs to a certain class, right? So for factory A, we're going to say, well, what's the probability that we get 10 red out of 20 marbles if it came from factory A? Well, factory A produces 60% red marbles, so its probability of getting only, making 10 out of 20 is around 11.7%. We're going to multiply that by the prior probability. We're going to also balance that by the fact that, most of the bags come from factory A, 50 or half of the bags come from factory A, which is 0.5. We multiply those together, we get 0.0585, okay, 5.8, 5.9%. We do the same thing from class B. We take the likelihood of getting 10 red out of 20 marbles, and we multiply it by the probability that the bag came from class B, which is 25%. So we multiply those together, and we get around 4.4%. We do the same thing for class C, 11.7% multiplied by 25%, 6 out of 24, and we get something around 2.9%. Okay, 0.029. Okay? And so these are the numerators for each of these things. Okay. Now, if I add these up, these things do not add up to 1. Okay, and that's where the denominator comes in. Okay, so the denominator is basically a scaling factor so that the resulting probabilities will add up to 1, okay? Because that's kind of a rule. So the denominator, which is just the probability of getting x nu, is the probability of getting the observed values in x nu regardless of the class label, right? So using kind of the law of total probability, we're just going to look at the numerator value across all the possible classes, because the pouch has to come from either one of those factories, factory A, B, or C, okay? And so if we just add up the numerators across all 3 possible classes, all 3 possible outcomes, this adds up to around 13%, 0.1319, okay? And so that's going to be our denominator, right? And what this will do is by taking each of these things and dividing by the denominator, okay, it's going to kind of basically scale up our values, right? So the probability of getting class A, given that the pouch produced 10 red out of 20 marbles, is going to equal basically the probability of getting 10 red, given that class A has p equal to 0.6, which is the likelihood, right? And that's the binomial probability. We're going to multiply that by the prior probability that comes from factory A, okay, which is we said is 0.5, 12 out of 24. And then we're going to divide that by the probability of just getting our data of 10 red regardless of the factory, which is going to equal the sum of the numerators, right? So when you do this thing, you get something around 0.444. Okay, and we do this for the other things, okay? The probability of getting 10 out of 20 for here, you go through the calculations. What's the probability of getting 10 red if the probability of getting red is 0.5 multiplied by the prior probability that it comes from factory B, okay? And so, you know, this has a higher likelihood, but the prior is a little bit lower. And so when you do that, you get 0.33. And then when you do it for class C, the probability of getting 10 red if the probability is 0.4, that's the kind of the property of the class, multiplied by the prior probability of factory C, okay? So we get this multiplied by 6 out of 24, and we get something like 0.222, okay? So, you know, when you take each of these numbers and you divide by the denominator, which is the sum of the numerators, you know, you're going to get 3 numbers that add up to 100%, okay? So our test case is 50% red, okay? And so again, you know, if we were to base our classification only on the fact that it was 50% red, we would have picked factory B, okay? But with the Bayes classifier, we take into account the prior probabilities, okay, where, you know, there were more bags from factory A than the other bags than factory B or C, okay? And so when we multiply this, okay, the likelihood calculations show us that, you know, that getting 50% red from a factory that produces 60% red is not an unlikely outcome. And so when you do the final multiplications, where you combine the likelihood and prior probabilities, factory A ends up being the most probable class, okay? Factory A has a 44% probability, factory B is 33%, and factory C is 22%, okay? So it turns out, you know, if you take into account kind of the fact that factory A produces more marble bags than any of the other factories, factory A still ends up being kind of the most probable class. All right. There were, maybe I'll just pause here and just kind of make sure we're okay with, I guess, these resulting calculations. Are we okay with how we got 44% here in kind of all of the steps? I guess if you're feeling good, give me a little green check. Otherwise, you know, throw in a question in the chat. And then let me also give you the first quiz answer. So for week 4 Monday, your first quiz question is E as in elephant, okay? E as in elephant for your first quiz question, E, the letter E. All right, So I hope this is good as far as the understanding where this comes from. Okay. There were a few assumptions that we're making. Okay. So one thing is that after we tallied up the data, I didn't bother showing the actual data from this made-up scenario. Is that we're assuming that the maximum likelihood estimate are the proportions of red marbles at the factory, right? So basically we dumped out we had 24 bags of marbles, and we dumped out the 12 that came from factory A, and we said, okay, when we dumped out the 12 that came from factory A, 60% of them are red, and therefore I believe that factory A produces 60% red marbles, okay? And we're just assuming factory A has a filling probability of 0.6 red. Now we could relax that with a fully Bayesian approach, and we can say, well, maybe it's 0.61 or maybe it's 0.58 or something like that. But that would make things more complicated, and it's beyond the scope of what I want to cover in this class. Okay. And then the other big assumption was that in our training data, 12 out of the 24 bags came from factory A. So we said the probability that a future bag comes from factory A is going to be 12 out of 24, 50%. Okay. So the big assumption there is that the sample that we have is representative of the class proportions in the population, right? Because my sample was 50% class A, I'm assuming that the population is also 50% class A, okay? That might not be a good assumption, okay? So, for example, if somebody works for this factory or for the company, and they say, oh yeah, we actually, all three factories produce an equal quantity of bags, right? Factory A produces a bunch of marbles, factory B and factory C, they all produce the same amount of marbles over the course of a year. So there's no reason to believe that factory A should make up 50% of the bags. So in that case, this prior probability, using that person's knowledge, we would just give factory A to be a 1/3 probability, okay? Because that person has kind of some knowledge of the process, and that would get incorporated in that prior knowledge or prior probability, okay? And so, so this is where the Bayesian classifier and Bayesian statistics, sometimes people object to this because you're able to take into account kind of prior knowledge, and it's depending on who's the one creating the models and the assumptions, they might have different opinions on what the prior probability should be. Okay, but I actually think that's a feature of Bayesian statistics, or even this Bayesian classifier, in that if you have knowledge about something, you want to incorporate that into your model, and you don't want to just ignore it and say, well, even though I know this is how it works, we're going to look at the data and only the data. Okay, it's good to mix in kind of some prior information, right? So this I just wrote: the situation in your domain knowledge will affect how you model your prior probabilities. Okay, so we said factory A has a probability of 50% because in our training data, 12 out of the 24 bags came from factory A. But maybe you know something about the process, and then you can incorporate that. Okay. So here's another example. It's the same example, but this time when we opened up the pouch, okay, there's 20 marbles, and only 6 of those marbles are red. Okay, only 6 of the marbles are red. And so when we say, well, what's the probability that this comes from factory A, or this one comes from factory B, and this one came from factory C, then what happens is that, look at these numbers, okay? Factory C has the highest likelihood, right? Because if it came from factory A and factory A is 60% red, then it's very unlikely, there's a low likelihood that it's going to produce a pouch where only 6 out of the 20 marbles are red, where only 30% are red, right? If factory A produces pouches with 60% red in general, could it produce a pouch where only 30% red? It's possible, but it's pretty unlikely, right? And that's going to be reflected in this likelihood. When you do the binomial probability, this calculation is going to be quite low, okay? On the other hand, factory C is going to have the highest likelihood because factory C produces pouches where 40% are red. So what's the probability that it's going to produce a pouch where only 30% are red? You know, it's not the most likely outcome, but it's also, it's not that unusual for factory C where its probability of red is 0.4. So we do this calculation, okay? And even if we multiply it by the prior probabilities where factory A is the most, has the highest prior probability, after you take into account the data that appears, it's got kind of the lowest value here. And so the numerators end up 0.002, 0.009, and 0.031. And when you add up the numerators, that's going to form our denominator. And the overall class probabilities end up being, it's only got about a 6% chance that it came from factory A, or it's got around a 72, 73% chance that it came from factory C. And factory B is something in between, around 21, 22%, okay? So we get around a 73% probability that it comes from factory C based on the fact that the pouch is only 30% red, okay? So technically any of these things could produce this pouch, but definitely factory C is the most likely candidate because factory C has kind of a filling probability of 0.4 rather than something higher. Okay, so the likelihood of getting only 6 out of 20 marbles is very low for factory A, where the filling proportion is 60% red. Okay, so factory A is very improbable, whereas factory C makes it the most probable class assignment. All right, is this okay for the Bayes classifier? This kind of the working through here. Please make sure you understand this because this is going to form the foundation for what we do with kind of the moving forward when we do like mixtures of multivariate Gaussians. So maybe I'll just give you an opportunity to ask questions or anything like that, or maybe this feels good for everybody. Okay, well, no one's saying anything. All right, so we'll go forward, and what we're going to do is we're going to look at the multivariate Gaussian or multivariate normal distribution. Okay, and so the multivariate normal distribution is this, and let me see. Let me just kind of pull up a picture. There's some nice pictures of this, okay? And so this is from Wikipedia. Okay, so basically you've got, this is a multivariate normal in 2 dimensions. And overall it produces this thing that looks kind of like an ellipse. And the idea is if you look at just one of the variables at a time, look at y only, it follows a normal distribution. If you look at x only, it follows a normal distribution. Okay, so if you kind of, I don't know, if you imagine these are like grains of sand or something, and you tilted it so they all fall in the x-axis, you know, you'd get a normal distribution here. If you dumped it the other way, you get a normal distribution the other way. And here there's some correlation, and so we get this ellipse. Okay, if you kind of create a joint plot, it looks like this. It looks kind of like a hill. Okay, I don't know. They all kind of have similar This is two separate normal distributions and things like that. Okay. Let me see if there's another. Right. Okay. So here's this is one where there's no correlation, and there's negative correlation, and this is stronger negative correlation, and the ellipse just gets kind of more and more pronounced. All right. So this is kind of the diagram, and to represent the multivariate Gaussian distribution using vector notation, this is what it looks like. Okay. Now, if you compare this PDF, right, and so the PDF of the multivariate Gaussian looks a little intimidating at first, but it's not all that different from the PDF of the normal distribution, the regular old normal distribution. If you look at the PDF of this, can I zoom into this? Well, that's okay. So here's the PDF of the normal distribution, and you can see there's a lot of parallels here, right? So here it's 1 over root 2 pi, and here this is 1 over basically root 2 pi, but raised to the d dimensions. Okay, so if it's one dimensional, okay, it just becomes root 2 pi, but then if it's like 2 or 3 or 4 dimensions, then it's d over 2 raised to that power. Okay. Sigma is the square root of the variance, okay, and that's what we have here. Okay, this capital sigma is the variance covariance matrix, okay, the covariance matrix of your of the x values, okay, and so this is kind of the square root of the variance matrix, okay, or the variance matrix raised to the 1/2 power. It's technically the norm of that is our sigma, and then we have exp raised to the -1/2, okay. And here we have x minus mu over sigma quantity squared, okay? And we have kind of the vector or the matrix equivalent of that, right? So x minus mu quantity squared can be expressed as x minus mu transpose x minus mu. That's how we would express like a quantity squared in vector notation. And then divide by sigma, or divide by the variance, because this is, if we expanded this, it'd be x minus mu squared over sigma squared. Dividing by the variance here is, there's no such thing as division of a matrix, but you can multiply by the inverse of a matrix. So you have sigma inverse here, okay? So, you know, when you first look at this, it feels a little bit intimidating, maybe. I don't know, maybe it totally feels fine for you guys. But if you could just think back to the normal distribution itself, it's actually, there's strong parallels between the normal distribution and the multivariate normal PDF, okay? So just keep in mind, this is vector notation. So mu is the vector of means, okay? Same dimensions as x, okay? The dth element tells you the mean of x sub d, okay? And then sigma is the d by d variance covariance matrix, right? So it's kind of the expected value of x minus mu squared, right? So what's the norm for sigma on the denominator? This thing here? Yeah, this is, oh, I'm sorry, not the norm. It's the determinant. Sorry, I said the wrong thing. This is the determinant of the matrix. I apologize. I said the wrong thing. This is, yeah, not the norm, the determinant of the sigma matrix, okay? Which kind of turns the matrix into a scalar value, right? It's like the, okay. And all right, and so when you talk about the variance covariance matrix, okay, the diagonal is the variances, okay, and then the off diagonal elements are the covariances, right? And so if the off diagonal elements are 0, then that means the x variables are independent, okay? And if the x variables are independent, technically the multivariate PDF can just be factored into a product of univariate Gaussian PDFs, right? So you have a univariate normal distribution in x, and if you multiply that by univariate normal distribution in y, you would get a multivariate Gaussian normal distribution. It's just that your variance covariance matrix would be a diagonal matrix. All right, and so I can generate data in R from the multivariate normal distribution, and we can do this just using, there's a library or a package called MVT-norm for multivariate normal. Super useful. Excuse me. And so here I'm going to generate data from 3 multivariate normal distributions. Okay, the first one has a mean. This is all 2-dimensional data. The first one has the mean is at 2, 3, the coordinate 2, 3, and the variance covariance matrix is the matrix 3, 0, 0, 1. Okay, meaning it's a diagonal matrix. X has a variance of 3, x1 has a variance of 3, and x2 or y has a variance of 1, and then there's no covariance between them. Okay, the off diagonals are 0. Okay, mu, the second class, its mean is 0, 0. Okay, and the diagonal, the sigma matrix is the identity matrix, so it's 1, 0, 0, 1. So X has a variance of 1, Y or X2 has a variance of 1, and there's no covariance between them. And then the third class, C, has a coordinate, a mean of 2, -2, and it's got variance matrix 3, 2.5, 2.5, 3. Okay, so its variances, X1 has a variance of 3, and X2 or Y has a variance of 3, and then there's covariance between these two of 2.5. Okay, and I'm going to generate 30 values from each of these classes, and to generate 30 random values, I use R MV norm. So right, to generate random normal values, you use R norm, and if you want random multivariate normal, you use R MV norm. Okay, random multivariate normal, MV norm, and then I'm going to bind them all together in X. Okay. And just to kind of illustrate this, I'm using a package called Ellipse, which allows me to draw ellipses. Otherwise, it's just going to draw the dots. And I kind of wanted to show you the ellipses. And so this is what our data looks like. Okay. And so from class A is the red. It is centered at 2, 3. Okay. So 2, 3 is right here. And X1 and X2 are independent, okay, and there's a normal distribution here, okay. Class 2, which are the blue dots, is centered at 0, 0, and I've got 30 random dots, and they're coming from here, and this is kind of our, the ellipses are circles because they have the same variance in the X and Y directions, or X1 and X2 directions, and there's also no covariance. They are independent of each other, so the what do you call these things? The axes of the ellipse, which is really a circle, are perpendicular to each other. Okay, and then class C, which is in green, okay, is centered at 2, -2, which is down here, and there's covariance between them, so we get basically a diagonal ellipse. Okay, and this is what it looks like here. Is this okay as far as generating the data from 3 multivariate normal distributions? Are we okay with kind of what these ellipses represent? They're kind of like, I think I've drawn kind of the locations of the, you know, the 40%, 65, 80, 90, and 95% levels here. Okay. All right, so this is kind of the dots are our simulated data, okay? And so what we're going to do is we are going to we're going to use the Bayes classifier, okay? Now, we generated the data ourselves, so we know what the mean and the variance matrices are of the of kind of the multivariate normal distributions that produced our data, okay? So we know these things, but what we have to do is we have to pretend that we don't know these values, right? Because what we want to do is, the situation that we're trying to emulate is we don't know the parameter values that generated our data. We're going to just look at our data, our training data, and based on this training data, we have to guess what that process looked like. And based on that, we're going to take a new observation and try to guess what class it belongs to. Okay, so we do know the class labels. So we do know that we have red dots and blue dots and green dots, but we don't know the mean and the variance matrices. Okay, we don't know the mean vector and we don't know the variance matrix of these things that produced it. Okay, and so we're going to estimate those. Okay, so kind of the maximum likelihood estimate of the mean vector is just the sample mean vector. Okay, so you just take I'm sorry, you take up the x values, you add them up, okay, and then you divide by n, okay, and that's going to be your mean vector. So n sub c is basically, you just do it for the values that belong to that class, okay, so it's just the mean of the observations that belong to that class. I think that makes perfect sense, right? So all I'm going to do is I'm going to just take my x values in A, and I'm going to just ask for the column means, okay? And so, you know, when we generated the data, we know that class A has a mean of 2, 3, mean of 2 and 3. When we take the column means, we don't get exactly 2 and 3. We get 2.26 and 2.82. So kind of close to 2, 3, but not exactly so, right? B, when we generated it, had a mean of 0, 0, okay? And if we take the mean of our observed data, we get 0.3 and negative 0.1. And then class C, when we generated it, had a mean of 2, negative 2, but because we have random data, we're getting 2.25 and negative 1.19. I'm sorry, negative 1.9. And so these are the estimated means based on the data that we have, okay? And then when you do the variance, okay, technically for the variance matrix, the maximum likelihood estimate is 1 over n rather than 1 over n minus 1, okay? But the maximum likelihood estimate is going to be biased. You guys had to prove this in like 100B, right? Where the 1 over n produces a biased result because you're using this sample mean to estimate it. And so if you don't do it, you have to use the Bessel's correction, 1 over n minus 1. So anyway, we'll just go ahead. We'll just use the sample variance, okay, which can be found this way. And luckily for us in R, we can just ask for the variance of a matrix, right? You just say, what's the variance of a matrix? And it produces, you know, your variance covariance matrix, right? And so here, when we generated it, the variance covariance matrix should have been 3, 0, 0, 1, okay? And our sample variance matrix is close to that, but not exactly that, okay? We get 2.98. This should be 0, it's a little bit off, and this should be 1, it's a little bit off. Same things for B. B was the identity matrix 1, 0, 0, 1, and it's close to that, but a little bit off, right? And then this one's kind of the most off, but I think when we said it was 3, 2.5, 2.5, and 3, and we're getting something quite different, but that just happens to be just what we get here, okay? And so I'm going to plot the estimated contour lines. So if we estimate show what the lines are that we've estimated as far as, you know, what are the normal distributions, what normal distributions generated our data, this is what we estimate, okay? And so this is based off of the data that we observed, and we can see, oh yeah, you know, this fits kind of the mean of the blue dots a little bit better, right? And this fits the mean of the green dots a little bit better, and the mean of the red dots a little bit better, okay? Let me go back. What slide is it? Okay. So this is, the black lines represent the distributions that I use to generate the data, but because of random sampling, I just happen to get some blue dots that aren't quite centered here, okay? And I happen to get green dots that aren't quite centered here, and I happen to get red dots that aren't quite centered here. And so when I estimate them, the estimated ones kind of fit the observed data a little bit better, right? So if I look at this versus this, we can see there's a little bit of difference. And if I plot them over each other, we can see how much they deviate by, okay? And again, we don't know, when you are looking at the data, you're not supposed to know the population that generated the random sample of data that you have, okay? And so we're gonna go off of this, okay? Which is a little bit different from the true values, okay? But this is what we have to go off of, right? You have to go off of your sample because you don't know the population that generated your data. So anyway, this is what we're gonna use. And using this, we are going to use the Bayes classifier, okay? And so why don't we take a short break? We'll take 5 minutes, maybe. I think at 1:58. Let's come back at 2:05, and then and we'll just apply the Bayes classifier to this to calculate kind of probabilities of new data points and things like that. Okay. All right. So we'll let me pause the recording. Okay. So we left off and we said based on the data that we observe, we create estimates of kind of the normal distributions, right? And that's easy to do because the data are labeled, so we know exactly what points belong to the red points, which points are blue, and which points are green. And based on this, we say, all right, what distribution, what are the properties of the distribution that generated the blue dots? And it's going to look like this. Okay, what are the properties of the distribution that generated the red dots? You know, we're assuming it's multivariate normal, and this is what we get. Okay, so now we have a new test case, right? So I'm going to put in test case at 0, 0, and we're going to say, what class does this dot belong to? Is this test case, is this a blue dot, a red dot, or a green dot? All right, so which class do you think generated this test case, right? So we look at this and we go, all right, you know, this is obviously going to be a blue dot, right? So, but we'll do the math to kind of back up what our eyes tell us, okay? So I come over here and we are going to do the Bayes classifier. So the Bayes classifier, again, just like we did with the pouches and the factories, here we're gonna do it for the multivariate Gaussian, okay? And so we say, what's the probability of getting this test case? 0, 0, the test case value 0, 0, that's our likelihood. If we assumed it belongs to class C. So, you know, what's the probability that the red distribution will generate this case 0, 0? What's the probability or likelihood that the blue distribution will generate this test case 0, 0? What's the likelihood that the green distribution will generate this test case 0, 0, right? Okay, so that will be our likelihood. The prior probability is going to be, well, before we even looked at this test case, I just said, hey, I'm going to generate a new dot. We're going to say, well, what's the probability it's going to be red, blue, or green? Okay, that's the prior probability. And then the marginal is going to be, you know, what's the probability of getting 0, 0, regardless of class label? And we can find that just by summing the numerator across all possible classes. Okay, so the likelihood is going to be found using the normal PDF, right? So our data values is 0, 0, okay? And so I can calculate this using the normal PDF. And so for class A, okay, I've got the mean x bar is x bar of A is you know, our estimate of the mean, and the variance of A is the sigma matrix, okay? And I can calculate this using the PDF of the normal distribution. So I've got 1 over 2 pi raised to the dimensions, which is 2 dimension over 2. Okay, so just raised to the 1, multiplied by the determinant of that variance matrix raised to the 1/2 power, times e raised to the negative 1/2 times x minus mu transpose, okay, multiplied by the inverse of sigma multiplied by x minus mu. I run those calculations and I get 0.0008795. 0.0008795. All right, now this is kind of a pain to do. Luckily for us, R has the density function, right? Density for the multivariate normal, and you just plug in your test case, which is 0, 0. You plug in the mean vector, which is x bar sub a, and your sigma matrix, which is variance underscore a. And when you calculate that, you get the exact same value, 0.0008795, okay? So these two values are exactly the same. So yes, you can use the normal PDF and do it manually, all right? Or you can just use the multivariate normal density function in R, right? And so, of course, because we're lazy, we should, not because we're lazy, but because somebody else programmed this for us, we should just use the built-in function, right? Like you could calculate the normal density, but why? Why would you when you can just use dnorm or dmv norm? Okay, so we're going to use this for each of the classes, and we're going to find the likelihood that it came from class A, the likelihood that it came from class B, and the likelihood that it came from class C. Okay, and this lines up exactly with what we anticipated, and we say, you know, what's the likelihood that red generates this point? It's pretty low. Blue generates this point, pretty high. Green generates this point, very low. Okay, so this is what we have. Okay, 0.008, 0008, 0.165, and 1.6 times 10 to the negative 5. Okay, as far as the prior probabilities go, as we have it, you know, in our training data, we have 90 observations total, and 30 came from A, 30 came from B, and 30 came from C. Okay, so the prior probabilities are going to be 1/3 for each of these. Okay, so because all three classes have the same prior probability, technically we don't even need to include them because they're all going to cancel out. They're going to cancel out in the numerators and the denominators. But just for completeness and to stay consistent with the Bayes rule formula, I'm going to include them. But I'm going to just say prior A, prior B, prior C are all equal to 1/3. Okay, and that's just because in my training data, 1/3 came from A, 1/3 came from B, and 1/3 came from C. Okay, but again, if you had set up your training data in a different way, where like 90% came from A and 10%, 8% came from B and 2% came from C or something like that, you'd want to set it up that way, right? Okay, and then the marginal is going to be found, the denominator is going to be found by summing up the numerator, right? So I'm going to take the likelihood of A times the prior of A, which is the numerator for class A. I'm going to add the numerator for class B, which is the likelihood times the prior, plus the numerator for class C, which is the likelihood times the prior. Okay. And again, technically the priors in this case will all cancel out because they're all 1/3, but we'll just do that. Okay. And so the resulting probability is equal to the likelihood multiplied by the prior divided by the marginal. Okay, so I hope this is okay. The likelihood, again, we found using the multivariate normal density. The priors we just set to 1/3, and the marginals we summed up the numerators, which is the product of the likelihood and the prior for all of the classes. And so the posterior probability using Bayes' rule is going to be the likelihood of class A multiplied by the prior probability of class A divided by that marginal probability, so that everything sums to 1. And we get 0.005, okay? So about 1/2 of 1%. The likelihood for B is 0.9946 or 0.995, so 99.5%. And then the likelihood times the prior for C divided by the marginal, the posterior probability of class C is almost 0, okay? 9 times 10 to the negative 5, so 1 in 10,000, somewhere around there. Okay, and so as we expected, the probability that 0, 0 belongs to class B is going to be the highest with around a 99.5% probability. Okay, is that all right? No, okay. All right, let's try out this one. Okay, so here's another test case. This one's at 6.2, okay, the location 6.2. And so just kind of based on this picture, what do you think is the most probable class? What do you guys think? So we've got red, blue, and green. Or I think it's A, B, and C. Yeah, okay. So it looks red, right? So probably the two highest ones will be red, followed by green, and blue is the least likely, right? So this is at least within kind of the circle for red, okay? And it's kind of just outside the circle for green, and it's like super far away for blue, okay? I'm not familiar with divergence. So, okay, so anyway, here we do the calculations here. So our new point is 6,2. So this time they all fit on one page, okay? And I just did the likelihoods using the multivariate normal density, okay? So I just say DMV norm, X nu, X bar A, variance of A, so on and so forth, okay? The prior probabilities are all just 1/3, and the marginal is gonna be the sum of the likelihood times the prior for each of the 3 different classes. And so for the probability that it belongs to class A is the likelihood times the prior divided by the marginal. You get around 79%, 79.5%. Likelihood that the posterior probability that's B, likelihood times the prior divided by the marginal, ends up being 3 times 10 to the negative 9. So very, very, very low probability. And then the probability that belongs to class C, right around 20%. Okay, so it's basically 80% A, 20% C, and pretty much 0 that it's B. Okay, so class A has the highest probability. Right? So that's what we have here. What about this one? Okay, so here I put in -5, 1, and we say, well, is it going to be A or is it going to be B or C? And so this one will end up being kind of a lot closer, I think, between the red and the green case. Just kind of looking at the picture. Is this red? Is this green? And so we do these calculations. Okay. So again, this is all found by doing the likelihood times the prior divided by the marginal for each of these things. Okay, likelihood's found using the multivariate normal density. And we get it's around 39% A and about 61% C, okay? So it's a lot closer to being fairly even here, okay? Whereas, you know, the probability that's class B is still pretty close to 0, okay? All right, and here's one where I kind of put it close to all of these. So what do you guys think? Red, blue, green, based on these, based on this graph? Is all of them green? Okay. Well, let's see. So if you look at the ellipses, it's most inside the red one. It's just inside the green one, and it's just outside the blue one. So let's just take a look. Okay. And actually, it turns out when you do the calculations, we're getting something close to 30% each. Okay, this is 2.53, 0.37. So I'm getting around 31% A, 36% B, 33% C. So this is one, you know, it's kind of at the intersection of all of these points, and they end up having, you know, fairly equal probabilities. Okay, I mean, obviously not exactly the same, but fairly close to each other. Okay, and I hope this kind of makes sense here in terms of like, you know, what we're getting in. And again, keep in mind that these ellipses are just estimated based off of the data that showed up in our sample. Now, if somebody else had collected data from the original generating process, right? So this is the original process that generates the data in black here. You know, we might get a different set of dots. And if we get a different set of dots, our estimate of the curves and the estimate of the distributions would be different, and our answers would be different. So a lot depends on kind of the data that you observe, right? That's the whole idea of training data. You're relying on that. Okay, so, you know, in summary here for the Bayes classifier is that, you know, the probability that an observation belongs to a particular class is going to be found using Bayes' rule, which is done by the likelihood multiplied by the prior divided by the marginal probability. Okay, and again, the way we find the marginal is you take the numerator, which is the likelihood times the prior, and you sum that up across all possible classes. Okay, the likelihood is the probability of getting your data if you assumed it came from a specific class, and then the prior is often equal to the proportion of observations that belong to class C in the observed data. But if you knew something else about the process, you can do something else here. All right, and so that's the Bayes classifier. And what we're going to do now is we're going to talk about the naive Bayes classifier. Okay, so again, here is the Gaussian, the multivariate Gaussian distribution. Okay, and if the off-diagonal elements are 0, then this normal distribution, this multivariate Gaussian distribution, can be factored into a product of univariate Gaussian PDFs. Okay. So when we talk about the naive assumption in the naive Bayes classifier, what we are saying is that all of the x variables are going to be assumed to be independent of each other. Okay. Now this assumption is usually wrong in that the x variables are frequently related. There's frequently covariance between the x variables. Okay, so why would we want to make the naive assumption? Okay, well, the reason for this is that it is often difficult to get reliable estimates of the covariance. Okay, so if you have, you know, when you only have a few variables like x1 and x2, getting an estimate of the covariance is not going to be too hard, okay? But if you have many variables, okay, to get accurate estimates of the covariances, you need lots and lots and lots of observations, okay? And so, and those estimates of covariances could be themselves will have high variance just depending on your random samples, right? And so what the naive assumption is we just say, I'm not even going to bother trying to estimate the covariances. We're just going to assume everything is 0. That the covariances are 0. Everything's independent, okay? This is not going to be correct, but it certainly simplifies our life, and it can still produce, you know, useful results here. So, you know, for example, you can use the naive Bayes classifier for document classification. So in document classification, right, you've got a document with a bunch of words, and you want to say like, this journal article is about politics, or this article is about space, or this article is about, I don't know, climate change or something, right? And you want to be able to classify the documents into different categories here, okay? In that case, the variables will be the words that appear in the document, okay? And we know that based on the structure of language, certain words are more likely to appear together than other words, right? Like if you're, I don't know, if you're talking about space, you know, talking about stars and night and galaxy, like stars and galaxy will have a higher covariance than say galaxy and politics, right? Whereas, you know, politics and government will have a higher covariance, okay? Like certain words are more likely to appear together. So politics and government will have a higher covariance. Stars and galaxy will have higher covariance. Politics and stars, or politics and galaxies, probably lower covariance, right? But how many words, how many variables do you have, right? In the English language, I don't know how many hundreds of thousands of words there are, and maybe you don't have all of the words represented, but you might have thousands of different words in your kind of collection of documents, your corpus here. And then you'd have to find a covariance between every single combination of words. That's going to be really, really, really hard to do, okay? And so it's going to be just a lot easier to just say the words aren't related, okay? That the words just appear independently. And that's wrong, right? We know stars and galaxies are more likely to appear in one document, and politics and government are more likely to appear together in another document. But instead, we can just treat everything as independent, okay? And we can just say, well, how often does the word politics and how often does the word government appear independently? And we can just kind of use those counts. And if you have a document that has the word politics frequently, it's probably a document about politics and stuff like that. And if you have a document with the word galaxy many times, probably about space, okay? And so we're not gonna bother trying to estimate the covariance between all of the words in the English language. That's probably close to impossible to do, right? So that's where the naive Bayes assumption comes in. We're just going to assume that everything's independent. Sorry, this should be an approximation sign, okay? Whereas this thing, or I guess if we assume that everything's independent, the equal sign is fine, okay? So if we assume that that this variance matrix is diagonal, then we can simplify this thing into a product of univariate normal PDFs, okay? Is that all right? So we're gonna take the multivariate Gaussian and just simplify it to a product of univariate normal PDFs, okay? Because we're saying that the variance matrix is a diagonal matrix. Okay, so if we take our simulated data, this is what the true distribution that generated it is, okay? In our simulated data, these distributions, the red and the blue distributions, were already, the x1 and x2 were already independent. But the green one had covariance. When we say that there's no covariance between them, okay, what's going to happen is that the major and minor axes of the ellipse will be perpendicular, and the axes of the ellipse will now be parallel to the axes of the graph. Okay, and so here we can just calculate the mean of each variable. So we can say the mean of x1 is just going to be the mean of the first column for the class A observations, and the class B observations, and the class C observations, and things like that. So we're just working through the means one variable at a time. So we're not going to get a vector of means. We're going to just get a bunch of univariate means for x1 in each of the classes and x2 in each of the classes. Okay, and then we do the same thing for the variances or the standard deviations. We just do them one at a time. So these are just scalar values. These are not going to be a matrix, right? When you calculate the variance of both columns, you're going to get a 2x2 matrix. But here we're just going to calculate the variance of one column at a time, and we're just going to get a singular value. Okay. And so this is what the contour lines of the estimated distribution will look like under the naive assumption. Okay. And so we can see that for the green cluster, this one ends up quite a bit wrong, okay? In that the green cluster actually has a lot of covariance, but we are assuming that there's no covariance here, okay? And so we get an ellipse that you know, is not correct, okay? So if you compare this to the contour lines from the regular Bayes classifier, where we did estimate the covariance, okay, we can see that it's pretty close for the red and blue clusters, okay? So when we estimated the covariance for the red cluster using the covariance, there was a slight covariance, not a ton, a slight, and so it's a little bit off, okay? Same thing with the blue ones, okay? But it's most off for the green cluster. The green cluster is way off because there is quite a bit of covariance in the data, and we're kind of forcing it to be 0. And again, so the naive Bayes classifier is, you know, makes it, you're not going to get as good, it's not going to be as accurate if you had good covariance estimates, but again, getting good covariance estimates on a high dimensional data set is actually really hard to do. And so, you know, for a low dimensional data set, probably we could get decent covariance estimates even from a few data points. But with a very high dimensional data set like the English language, each word representing its own variable, it would be really hard, almost impossible to get covariance between every single combination of words. Okay, all right, so this is what I talked about with the naive assumption. There's no covariance, so the major and minor axes of the ellipse are parallel to the plot axes, okay? All right, and so here we're gonna put in the test case 0, 0, okay? And when we do this, you know, blue is gonna be the most likely, but then the green case will also be not super unlikely, okay? And so we follow the same rules, but this time the likelihood does not need to be calculated using the multivariate normal, okay? We can calculate the likelihood as the product of independent normal PDFs, right? So we can just take the normal PDF using dnorm and taking a product of those, right? So here, instead of finding the multivariate normal, I can just use dnorm and ask for dnorm of x1 and the dnorm of x2, okay, given the mean of x1 and the mean of x2, okay? So we're going to do this for A, B, and C. So I'm not using the multivariate dmv norm, I'm just using dnorm, but I'm multiplying it for x1 and x2. So it's the product of normal PDFs. Okay, is everybody with me so far? Is this so far so good? Using the product of just your regular old normal density, not a multivariate normal density. Okay, and so when we do this, you know, we still find the priors the same way, we find the marginal this exact same way, and we calculate these probabilities, and what we get is likelihood B, oops, okay. The probability of being B is the highest, but then the probability of C is next, so we got around 94% and around 5% and something a little bit less than 1% for class A, okay? Whereas, let me compare these results. Sorry, this got cut off here. So we're getting around 5% here, and that's because our picture looks like this. If I, can I open the same thing with just a different PDF viewer? Okay, so, you know, when we look at so this is the naive Bayes classifier. Okay, we see that, you know, this falls still kind of within the ellipses of the green of the green cluster, whereas over here this is very far away because here we're estimating the covariance, and so, you know, deviations in this direction would be reasonable, but deviations in this direction would be very unlikely, and so the fact that it exists over here makes it almost impossible to belong to the green cluster. And so, you know, when you get the resulting probabilities for the green cluster, it's you know, magnitudes lower, okay? Whereas over here we're getting something magnitudes higher, right? And so, you know, this is not a good cell. This example is kind of makes a case against the naive Bayes classifier. But again, in a lot of cases where you have high dimensional data sets, the naive Bayes classifier is very useful because trying to estimate that covariance matrix it can get quite difficult to do. Okay, we're going to end a little bit early today. I've already posted homework 4. I know you guys are still working on homework 3, but homework 4 is posted, and so and this starts off with classifiers. And on Wednesday we will take a look at k-nearest neighbors and take a look at support vector machines as a way for classification as well. And the rest of homework 4 deals with those. So in homework 4, you'll create a naive Bayes classifier for the iris data set, and I hope it's a fun and interesting exercise, and it should be good. Okay. All right. We'll end here a little bit early. Oh, did I give you quiz answers? I totally forgot about them. What did I? How many have I given you? I'll just give you all 3 of them. Okay, wait, hang on. Okay, the other quiz answers are quiz answer 2 is A as in apple, and quiz answer C. The third quiz answer is C as in cat. Okay, so you got E, A, and C. All right, so quiz answer 2 is apple. Quiz answer 3 is C as in cat. And that's it for Monday. So yes, homework 4 is startable, at least for the first exercise. So I've covered the naive Bayes and naive Bayes classifier, and you can get started on homework 4 with that. And then the other stuff for homework 4, the k-nearest neighbors and support vector machine stuff, will come in Wednesday's lecture. All right, have a good day, you guys, and we'll see you guys on Wednesday.
Professor, one quick question. You can end